Everyone are clear with the session's time scale. So last week we concluded the second week of the course where we started with the discussion on properties of cement. We listed chemical and physical properties. Okay, chemical properties we discussed in week 1 and we started with the physical properties in week 2, wherein physical properties are nothing but the end result of the chemical properties, and thus they are critical in determining the suitability of a cement for a specific application and ensuring a desired performance of the concrete. So that's why physical properties are important. We talked about different physical properties, those uh, different properties like normal consistency, specific gravity, soundness, fineness, setting time, and compressive strength. For these, we had a brief discussion. Then we talked about types of cement. So based on the composition of cement, cement class can be classified into different types, and these classification becomes important so that we can have a best suited cement type for a particular application need. In cement types, we discussed three classification. Based on ASTM, we talked about five types of ASTM type cement: type 1, 2, 3, 4, and 5. We talked about special purpose cement like high alumina cement, super sulfated cement, white cement, and expansive cement. And we talked about blended cements, where we talked about substitution of OPC with mineral admixtures like fly ash, ground granulated blast furnace slag, and silica fume. We saw the basic chemistry behind each of the type, and in special purpose cement we talked about so in ASTM types cement, we talked about type 1, which is a conventional OPC, type 2, which is a modified Portland cement, type 3, which is a rapid hardening Portland cement, type 4, which is a low heat Portland cement, and type 5, which is a super sulfate resisting cement. Okay, for each of the type, we saw the chemical composition and we saw what is making them act for a particular application. Then we came to special purpose cement, where we talked about super sulfated cement, hyaluronate cement, white cement, and expansive cement. And in blended cement, we first understood how blended cement came by looking into the history of hydraulic lime and volcanic ash. Then we just introduced ourselves to fly ash, slag, and silica fume, how they are obtained and why they show cementitious property. A much detailed discussion on into these in these blended cement we will discuss in the next week content when we'll talk about mineral admixture. Then we talked about aggregates that are used in concrete. Here we talked about classification of aggregate based on size, shape, and texture. And before this, we also talked about source, also like how aggregates are classified based on parent rock, igneous, sedimentary, and metamorphic, and other classifications like natural, manufactured, and recycled aggregates. In size, we talked about coarse and fine aggregate, how sieve analysis is done for grading aggregate. We saw numerical for calculating percentage retained, cumulative percent passing, and to identify coarse and fine aggregate content. Then we came to classification based on shape, where we saw six classes: rounded, irregular, angular, flaky, elongated, and flaky and elongated. We saw how the shape of the aggregate can affect the performance of concrete. And finally, we talked about the surface texture, where we had six classes: glassy, smooth, granular, rough, crystalline, and honeycombed and porous. Okay, so these were all, this was what we discussed in the last live session. Now, if you recall our discussion from the last week content, where we talked about why aggregates are used in concrete, there was one important point that was mentioned. They reduce overall cost of concrete by acting as a filler, minimizing the amount of expensive cement required. Okay, now if aggregates are acting as a filler, the more efficiently it will do the filling or packing, the lower will be the requirement of cement. And that is where packing density of aggregates come into play. Okay, so by packing density, we simply mean the ratio of volume of solid to the bulk volume of solid particle. Okay, and here the bulk volume is equal to the volume of solid plus volume of voids. Okay, now if I try to write this definition in a mathematical term, so how I can write? So it will be suppose I am denoting packing density by PD. So PD will be nothing but Vs upon Vb. Okay, so Vs is denoting my volume of solid and Vb is denoting my bulk volume. Okay, now I know Vb is nothing but Vs plus number of voids that are there in my bulk volume. So I can write this equation as Vs upon Vs plus Va. So Va is my volume of pores inside inside my given aggregate lump. Okay, now if I add here in the numerator, suppose I am adding volume of voids, I am adding and subtracting volume of voids. So what will happen? I can break this equation into two parts. First will be this part upon this part, and second will be this part upon this part. Okay, so first Vs, so first part will be nothing but 1. Okay, Vs plus Va upon Vs plus Va, that will become equal to 1 minus Va upon Vs plus Va I can write. So this is how I can write this equation. Okay. So what we did, we just took the simple definition of packing density and we broke it down into this equation. Now if you see, this is volume of voids and this is total volume. So this ratio, second term, is nothing but the porosity. That is the percentage voids in a system. So that is how this equation came into existence. So packing density is nothing but 1 minus porosity. Okay. So a higher packing density means smaller number of voids to be filled and vice versa. Okay. So if I have lower packing density, it means there are more voids in the system. Now, what are the benefits of having a higher packing density? So it will increase the workability. Okay, it increases the workability or strength of my concrete, and it will also improve the dimensional stability of concrete. How? Because it will reduce the paste demand, which in turn will reduce the drying shrinkage problem and thermal contraction and expansion issues. So that's why for a good high performance concrete, we need a optimum packing density of aggregate. Now, what size of aggregate we are taking can significantly affect the influence on the can significantly influence the packing density. So suppose we are taking a mixture of a single sized aggregate. By single size I mean, suppose I am taking only 10 aggregate or 20 aggregate or 4.75 aggregate. So I am taking a single sized aggregate and cement paste. Now to fill up all the gaps between the aggregate and to drive away the air voids inside the concrete, what I need my cement volume to be greater than the volume of gap within the aggregate skeleton. Okay, so I have an aggregate skeleton like this. Okay, these are single sized aggregate, suppose, and there will be gap in between. Okay, now if I want to fill up all the gaps in between aggregates, I need my cement volume should be greater than the gap between the aggregate. Okay, now, instead of single sized aggregate, suppose I'm using a multi sized aggregate. Okay, so what will happen? Instead of my cement filling the gaps between the aggregate, the smaller size aggregate will fill up the gaps between the larger size aggregate. And what this will result in? This will result in a smaller volume of gaps should to be filled within the aggregate skeleton by cement. Okay, so a multi-site aggregates has two implications. The volume of cement that is needed to fill the gaps within the aggregate skeleton will be reduced because some volume will be filled by the smaller sized aggregate itself. And if I keep my volume of cement paste the same, if I'm not reducing my cement paste volume, so what will happen? My excess of cement paste, there will be an excess of cement paste beyond aggregate filling, and that excess paste will help me to disperse the aggregate particles. So what will happen? The excess paste will go in between the aggregate particle, and they will provide a coating of paste on each aggregate particle, which will improve the workability of the concrete mix. Okay, so in this way, a multi-sized aggregate system will differ from a single-sized aggregate system. So simply saying, in a multi-sized aggregate system, aggregate by themselves are acting as a filler for their coarser version, rather than requiring cement paste to fill the voids. Okay, the same concept has been explained here in the image also. So you can see here in figure 1, you have a concrete composed of a single sized aggregate only. So you can see there is a large amount of voids that are present that needs to be filled by the cement paste. However, if I am using a multi-sized aggregate, what will happen? You can see here my smaller aggregates are filling the gaps between the larger aggregate. So what it will do, it will it will cause reduction in cement paste volume required to fill the gaps between the aggregate skeleton. And if I keep the cement paste volume same, if I'm not reducing, so what will happen? My cement paste will start coating the aggregates and separating the aggregate, and it will improve the workability. Okay, so this image was taken from this article that I have mentioned here. Okay, it is a very nice article, very small and nice article, like 10 to 12 pages content on particle density and high performance concrete. So if anyone is interested to read more about this concept, they can refer to this article. Okay. Now, if we try to understand the single sized and multi sized aggregate thing in mathematical terms, so for a single sized aggregate, the packing density will depend upon the arrangement of particle. Okay, and this can be done in three ways: simple cubic, body centered cubic, and face centered cubic. Now, what are these terms simple cubic, FC's body centered cubic, and face centered cubic mean? So, these are commonly known as different types of crystal lattice structures that describe how atoms are arranged in a crystalline solid. Okay, so in this figure, you can see how atoms, or we can say particle, or in our case, you can say aggregate, would be arranged in a lattice structure. So, we have a primitive cubic lattice in which all my aggregates are at the corner of a cube. Okay, so you can see on all the edges there is one aggregate. So this is known as cubic, simple cubic lattice structure. Then I have body centered cubic lattice where I will have all the aggregates on the corner and one aggregate in the middle. Okay, and I have face centered cubics, as name suggests. I will have all the aggregates at the corners also, and one aggregate at the face centers also. Okay, so this is known as face centered cubic structure. Now, how it will affect the packing density? So you can clearly see from the image, FCC. This is short for in short form. This is known as FCC. This is known as BCC, and this is just simple cubic. So FCC will have the highest packing density. Then there will be BCC, and then there will be simple cubic. Okay, so if I consider a perfectly spherical aggregate, the packing density of this lattice structures will come out to be, for simple cubic, it will be 0.52. For body centered cubic, it will be 0.68, and for face centered cubic, it will be 0.74. What this value means? So suppose this is 100% volume. If I consider the whole cube as a 100% volume, so 52% will be filled by my aggregates and rather will be voids. In this case, the percentage occupied by aggregate will increase, and in this case, the percentage occupied by aggregate will increase further. Okay. Now, actual packing density of a single-sized sphere will lie somewhere in between. Okay. However, with the multi-sized aggregate system, one can have a higher packing density that can go up to zero point 0.8 and above also. Okay. So, if we see a simple example of a multi-sized aggregate system by talking about a binary mixture of aggregate, so suppose we consider two aggregates, A and B, where B is coarser and A is finer. Okay, so my total bulk volume is represented by volume of pores plus volume of solid, and so my void ratio will be volume of pores upon volume of solid. Okay, so I can break this equation as in this form. Okay, So what I can do, I can write volume of pores as bulk volume minus volume of solid. Okay. And when I will divide this by volume of solid, so it will become V upon V solid minus 1. So this is how I can represent the void ratio. Okay, this is known as the void ratio, the ratio of voids in the total system. Okay, so if right now I consider both the systems separately, okay, B is separate, A is separate. So void ratio in A will be bulk volume upon volume of solids in A minus 1, and void ratio of B will be bulk volume upon volume of solids of B minus 1. So separately I can write the void ratio in like this. Okay. So here we are talking about void ratio. Earlier we said porosity. Both are different things, but we can understand they are representing the same concept. Okay. Here we are just talking about the ratio of voids in terms of solid, whereas porosity is the amount of voids with respect to the total volume. Okay. Now, if we can suppose I am adding coarse aggregate into fine aggregate, okay, I am using a multi-sized aggregate system. So, since we are adding B to A, what will happen? The total bulk volume will be bulk volume of A plus solid volume of B. Okay. However, the total solid volume will be solid volume of A plus solid volume of E. So I can write void ratio E is equal to bulk volume upon solid volume minus 1, and this I can write as bulk volume V plus solid volume of B, while solid volume, total solid volume will be solid volume of A plus solid volume of B minus 1. Okay. Now, suppose if we assume that the volume fraction of B, like solid volume fraction of B as X, and X here represent volume of solid volume of B upon solid volume of A plus solid volume of B. And we know that void ratio of A when there was no B is represented by this equation. So what we can do, we can simply write this equation as, so here I have this equation. Okay, so what I will do, I will separate this term upon this term separately I will write, and this term upon this term I will separately write. So what it will become, V upon VSA plus VSB plus VSB upon VSA plus VSB will be nothing but X. Okay, minus 1. So this is how this equation will convert. Now I need to have this factor. I know this equation also holds true. So what I will do, in the numerator, I will multiply and divide by VSA. Okay, I have multiplied VSA and I am dividing VSA. Okay, so, solid volume of A. So what will happen? This term, this term upon this term, V upon VSA, it will be nothing but EA plus 1. Okay, so what it will become? V upon VSA I can write as void ratio of A plus 1. Okay, into VSA upon VSA plus VSB will be nothing but 1 minus X. Okay, because I know X is this, so 1 minus X will be VSA upon VSA plus VSB plus X minus 1. Okay, so when we'll try to simplify this term, it will come out to be E void ratio of this multi-sized aggregate system will come out to be void ratio of A when there was no B times 1 minus X, where X is the volume fraction of B that we have added. Okay, so this is how void ratio will change if I will add a coarser aggregate into a finer aggregate. So you can see, as I will increase the amount of B in A, my void ratio will decrease. Okay. Similarly, suppose we are adding fine aggregate to coarse aggregate. So I'm adding A to B. So since we are adding A to B, total bulk volume of B will remain undisturbed. Why? Because A are smaller sized aggregate, they will occupy the gap between B. So they won't be increasing the bulk volume of B. However, this total solid volume will be solid volume of A plus solid volume of V. So I can write E as V upon V solid minus 1, and this I can write as V upon VSA plus VSB minus 1. And I know my X is solid volume of B upon total solid volume. X I am keeping the same. I am representing by this only. Okay, and I know what was the solid volume of B when there was no A. Okay, so similarly, how we did the break up of this equation here, we can do the similar thing here and we'll get this equation. How the or void ratio in my multi-sized aggregate system will depend upon the amount of aggregates that I am mixing and the original void ratio in my system. Okay, so we have two equations right now. One is when I have added coarse aggregate to fine aggregate, and one is when I have added fine aggregate to coarse aggregate. Okay, so my EX, my void ratio, can be represented by two lines. Okay, and these two lines will interact at a single point, that is, I am representing by X star. So X star will represent the binary mixture of the aggregates which will yield the minimum void ratio. You can see here I had A only and here I had B only. Okay, so my void ratio was EA here, EB here. However, when I start mixing A and B, what will happen? My void ratio will decrease. So this will represent my one equation, equation 1, and this will represent my equation 2. So both the equation are meeting at a certain point. Okay, and this point is known as the point where my void ratio will be minimum. So this will declare what is the optimum packing of A and B to achieve the minimum void in the system. Okay, we can represent the same thing, like we can convert the void ratio into packing density terms also. So we know packing density is nothing but volume of solid upon bulk volume, which is nothing but equal to 1 minus porosity. This derivation we have seen, and we know void ratio is V upon Vs minus 1. Okay, so inverse of this term is my porosity, packing density. I can write this term as 1 upon Pd. Okay, so if I will rearrange this, I will get this equation. So packing density is nothing but 1 upon 1 plus void ratio, and this is represented in this figure. So you can see here I have only A, so I have packing density of this value. When I have only B, I have packing density of this value, and when I'm mixing A and B, so you can see here how my fine aggregates are filling the gaps between the coarse aggregate, and here it is the optimum packing. My fine aggregates have completely filled the void gaps between the coarse aggregate, and I'm getting the maximum packing. And here also I can see my coarser aggregates are more in proportion, so my fine aggregates are not completely distributed in all the pores. I have a slight lower packing density compared to the maximum value. Okay, so this is how a multi-sized aggregate system works. Okay, so let's see few numericals here, how to calculate the packing density and how to find what should be my ratio of aggregates. Okay, so I have this the three questions. So first two are numericals, and third one is a simple objective question. So try to answer these questions. And in the meantime, if anyone has any doubt in the content that we have discussed till now, they can post their questions in the chat box. I will wait for a couple of minutes for you guys to answer the question, and then I will tell the answers. What is the difference between X, that is volume fraction of V, and EX? See, X is representing the solid volume. So suppose I have A and I have B. I have 40% of A and 60% of B in my total system. So my solid volume of B is 60%, like 100% I have volume. Suppose I have 100 meter cube of aggregates, out of which 60 meter cube is B size and 40 meter cube is A size. So that X is representing what is my fraction of B size of aggregate. So that is 60 upon 60 plus 40. So zero point 0.6. And void ratio with respect to X, this EX represent how this X, suppose instead of 60 meter cube B, I am taking 40 meter cube V, or I am taking 60 meter cubes, 80 meter cubes of V. So how with the volume of aggregates, my void ratio will change. So that is representing Ex. Okay, E as a function of X. So in mathematics, how we write now y as a function of x. So how y is changing when x is changing. So here we have written Ex. What is binary mixture? Binary mixture when we have two sizes. Okay, A and B. If I have ternary mixture, I have three size. And I have if I have more than three sizes, then we say multi-sized aggregate. Okay, I am freezing my screen right now so that everyone can see the questions. Yes, Prasanta, you can ask your query. Try to write in the chat box so that others can keep doing the questions. Okay, so let's see the answers now. So that because we have a lot of content to discuss, I will tell you how to solve this question, and then you can ask me if you have any doubts in the solution. So in the first question, what is written? I have a binary aggregate system consisting of coarse and fine aggregate. The void ratio of coarse aggregate alone is 40%, and the void content of fine aggregate alone is 30%. So this is my EB and this is my EA. Okay. If fine aggregate completely fills the void in the coarse aggregate, what is the theoretical packing density of the mixture? So this line here is important. What they are saying, if fine aggregates completely fills the void of the coarse aggregate, so this means they are talking about this point, the point of minimum, where void ratio will be maximum. When the void ratio will be maximum, when my fine aggregates are completely filling the voids between the coarse aggregate. So I can use this equation. Okay, because we told x star represents the binary mixture which yields the minimum void ratio. Okay, so I have this equation with me. Ex star is equal to Ea into 1 minus x star, which is equal to x star into 1 plus Eb minus 1. Okay, so I have this equation with me. I know the value of Ea. Ea is 0.3. Okay, A represents my fine aggregate. Okay, and I know Eb. Eb is zero point 0.4. Okay, so I know both the values and I have only one variable x. So this will become, if you break this down, it will be 1.7 times x is equal to 1.3. So my x will come out to be 76.5%, or you can write as 0.765. So this is my theoretical value of void ratio. This is my packing density, I can say. Okay, this will be the value of my x. Okay, void ratio. And then you can calculate the packing density because you know this equation. PD is equal to 1 plus 1 upon 1 plus E. Okay, so from that you can calculate the void ratio, packing density. Okay, so this is how we solve such question. Now, second question. 41 upon 71. Maybe it would be correct. You can do the calculation. Second, a binary mixture consists of 70% coarse aggregate having packing density 0.68 and 30% fine aggregate having packing density of 0.55. If the fine aggregates fills 80% of the voids of the coarse aggregate, what is the estimated packing density of the mixture? Okay, so we have given that we have packing density of coarse aggregate as 0.68. Now I know packing density is equal to 1 minus uh, void content. Okay, 1 minus porosity. Okay, so what I can write, my void porosity in my coarse aggregate is 1 minus packing density, it is 1 minus 0.68. Okay, which is equal to 0.32. Now 80% of my voids, porosity is what, nothing, representing my voids only. Okay, so 80% of these voids are filled by the fine aggregates. So from in 0.32, 80% are occupied by the fine aggregates. So 0.80 0.8 times 0.32 will be 0.256. Okay. Okay, so this much volume of my porosity is now aggregate by the fine aggregate. So what is my total solid content? It will become 0.68 that was initially there plus 0.256, which is equal to 0.936. So this is my total packing density of my mixtures, total solids that are there in my mixture, because there were 80% voids that is occupied by the coarse aggregates. I first calculated how much voids are actually there in the coarse aggregate, among which 80% is occupied by my fine aggregates. So this is my total solid content. So this is my total packing density. Okay. Third question. Consider a binary aggregate system where the coarse to fine ratio is optimized for maximum packing density. If an external compaction force is applied, what which of the following will most likely occur? Packing density will remain unchanged as it has already reached the theoretical maximum. Coarse particle will rearrange, allowing further densification. Fine particle migrate into the voids. Water demand of the mixture will significantly increase. So the correct answer will be B1. Why? Because if I'm applying some external compaction, so what will happen? My coarse aggregate particle will try to rearrange among themselves, and this can allow further densification. That is why compaction is actually done, so that we can densify our system furthermore. Okay, naturally my fine and coarse aggregate will try to arrange on their own, but if I am applying some external compaction, they can further consolidate and further densify the system. Okay. This question we'll discuss at the end. Okay. Your question is from week one session, so wait till the end of the this session and then I will discuss it with you. Any doubts in these three questions that I have discussed now? So first two question, and just try to revisit our discussion that we had just now. Okay, when you will revisit, you will get more clarity how this question was solved. Okay, it is just the simple application of concept and the formulas that we derived. Okay, and third question is based on compaction. So with higher compaction, there will further densify the system. Any doubts in these questions? If you have any doubts, you can also ask at the end of the session. Since there is no doubt right now, I will proceed ahead. Now, it is not like every time a multi-sized aggregate system will give you a maximum packing only. Okay, there are two negative effects of multi-sized aggregate system. One is known as loosening effect and the other one is known as wall effect. Okay, so now what is loosening effect? So loosening effect occurs when my small particles are that are added into a mixture of large particle, but the size of my small particle is not small enough to fill the voids between the large particle. So suppose this I have large particles like this, okay, and I need a finer aggregates which can fill the gap in between. This much fine it should be. Okay, it should have size of this much only. But suppose my fine aggregate of is of this size. So what will happen? It is too big to fit in the into the void between the large particle. So instead of filling the gap, what will happen? These particle, they will disturb the packing arrangement that was initially there, and they can, instead of decreasing the void content, they can increase the overall void space. This is known as loosening effect. Okay, so my fine aggregate should be fine enough to fill the gap between the coarse aggregate. If it is not fine enough to fill the gap between the coarse aggregate, then they can cause disruption of packing instead of densification of packing. And the second term is known as wall effect. So it refers to the disruption of particle packing that happens near the boundaries or wall of a container. Or in case of concreting, we can say molds. Okay, so near the molds, the disruption in packing that can happen. Okay, so particle near the wall, they can't efficiently occupy the space as they occupy in the bulk, because the wall causes it wall interferes in their ability to rearrange. And this effect of wall, which interferes in the ability of particle to rearrange, is known as wall effect. Okay, now it is not like you can take any two dissimilar size aggregate and you can achieve the optimum packing. Your aggregate should be of sizes such that they can fit in spaces with each other, and that's why we have grading of aggregate, which becomes important. Okay, so you can't take any two size of aggregate and achieve optimum packing. Your aggregate sizes should have a proper grading so that they can fill up spaces between each other, and that is where grading becomes important. Okay, so idea behind binary mixture can be extended to a multinary mixtures as well, to show that packing density improves with each subsequent size addition. Okay, so instead of two sizes of particle, if I will take four or six or eight sizes of particle, I can further improve my packing density. And grading of aggregate refers to the distribution of different particle sizes within the given sample. So in a given sample, what are different sizes of particle available, that is determined by grading of aggregate. For normal concrete packing, practical grading curves are proposed in the code to ensure proper range of size fraction in the overall aggregate system. Okay, so there are grading curves that are available in the codes that make sure that my size of there are appropriate size fractions in my overall aggregate system, which is properly filling the spaces rather than causing these loosening and wall effect. Okay, so it, we talked about this in the last session also. We have well graded aggregate, poorly graded aggregate, and gap graded aggregate. In well graded, we saw like in between larger particles, smaller particles were able to properly fill the void spaces, and that's why they are known as well graded. In poorly graded, there will be larger void spaces in between because they are single sized aggregate. And in gap graded, what will happen? Again, there will be only two sizes of aggregate and there won't be any like distributed size of aggregate. That's why they are known as gap graded. Okay. Now these grading curves that are proposed in standards, they are just graphical representation of particle size distribution of aggregate. And these curves are provided in standards such as ASTM C33, IS 383 and BS 882 to ensure consistency, optimized packing density, and to achieve desirable properties in concrete and asphalt mixtures. Okay, and these curves help engineers to select right aggregate gradation to balance strength, workability, and durability. So this diagram we saw in the last session also. Okay, where we saw how a uniform graded aggregate, a gap graded aggregate, and a well graded aggregate, they are represented. Okay, so in well graded, you can see different sizes of aggregate are uniform, like they are properly present. In uniform graded, you can see most of the aggregate are in this range, and in gap graded, you can see there is a higher aggregate quantity here and higher aggregate quantity here. Okay. Now this is table 2 from IS 383, Indian Standard of Coarse and Fine Aggregate for Concrete, and this table provides the grading requirement for coarse aggregate. Okay, it specifies the standard sizes of aggregate and their corresponding percentage passing through different IS sieves. Okay, so we have aggregate listed here as 20 mm, 40 mm, 10 mm, 16 mm, 12.5 mm, and 63 mm. We have grading limits, like for each aggregate size it specifies percentage of material that should pass through different various sieves to ensure proper grading. For example, for 20 mm, 100% aggregate should pass to 40 mm sieves, 85 to 100% should pass to 20 mm sieves, and 10 to 20% should pass to 10 mm, and 0 to 5% should pass to 4.75 mm. So these are grading limits. Okay, so if I have a bunch of aggregate available, based on its percentage passing, I can determine in which grade it belongs. It is 20%, 20 mm down, 40 mm down, 16 mm down, we can classify. Okay, and the purpose of this is to ensure that aggregate have a right particle size distribution so that they can achieve optimum packing. Okay, and these are used in concrete mixture design to select and verify aggregates that meet a quality or performance standard. Okay. Similar to coarse aggregate, we have a table for fine aggregate also, table 4 of IS 383, in which we classify fine aggregate into four grading scale: 1, 2, 3, and 4. Okay, you can see in this percentage passing through 300 micron size. In grading 4, there is maximum particle passing of aggregate through 300 micron size, and grading 1, we have minimum percentage passing through 300 micron size. This means that 400 grading 4 is the finest and grading 1 is coarser compared to other three. Okay, so in this way fine aggregates also we can classify into different grade, different zone. And we have table 5, which is all in aggregates. That means there are both coarse and fine aggregate combined, and if I want to grade them, so I can grade in two ranges: 40 mm nominal size or 20 mm nominal size, and for that different IS sieve designation and percentage passing have been mentioned. Okay. Now, to understand this aggregate grading, there are two terms that are most commonly used. One is fineness modulus and other one is surface modulus. So, fineness modulus is nothing but an index number, that is weighted average sieve number, that gives us a rough estimate of particle average particle size in a given aggregate sample. Okay, this is commonly used to categorize fine aggregate as coarse, medium, or fine, and it helps in mixed proportioning. How we calculate fineness modulus? So it is determined by adding the cumulative percentage retained on standard sieve size and dividing them by 100. Okay, we will see one numerical here so that you can know how this value comes out. But for now, remember this formula: cumulative percentage retained on a standard set of sieves divided by sum of the total sum, that is 100. Okay, and how we interpret the result? We interpret in terms of the value that we are obtaining. If my fineness modulus is less than 2.2, I say it is a very fine sand. Okay, which is generally not suitable for concrete. If my fineness modulus is between 2.2 to 2.9, we say it is a medium sand, which is good for concrete. 2.9 to 3.2, it is coarse sand, which is used for special application, and above 3.2 it is very coarse sand, which is not suitable for concrete again. So my fineness modulus should generally lie in this range. Okay, and higher fineness modulus reduces the water demand, lower fineness modulus increases the paste demand but also improves the workability. After fineness modulus, there is surface modulus, which specifies the specific surface area of aggregate, that is the total surface area available per unit volume or weight of aggregate. And surface modulus is determined by this formula: total surface area of aggregate upon total volume of aggregate. Now, where surface modulus will be used, it will be used to estimate the water demand and the workability of concrete. Okay, finer particles, they have higher surface modulus. Okay, they have more surface area, so they will have more water demand. And coarser particle have lower surface modulus, so they have less surface area, and thus they will have lower water demand. Okay, so if we consider our aggregate as simple sphere, okay, so specific surface area is nothing but surface area upon volume, so it will come out to be 6 by d. Okay. Now, here D is the size of my aggregate, but generally we don't know the size of the aggregate. We just do the sieve analysis. So we know sizes are in between two sieves. So like it is 10 passing, 4.75 retaining, or 4.75 passing, 2.6 retaining. We don't know the exact size. So that's why if we know that my aggregate is having a size between two sieves of diameter di and di minus 1, I represent the diameter of my aggregate as the geometric mean width of the two sizes. So under root of di into di minus 1, this is my diameter of aggregate, how I represents the diameter of aggregate. Okay. Now, since my sieves are arranged in a geometric progression, so I have like geometric progression is like this: 10, 100,000. Okay, so their ratio is constant. So since my c's are also in this size, so my specific surface area will always be reduced by a factor of 2 if I will take a higher c size. So this di minus 1, di will be equal to 2 times di minus 1. Okay, di plus 1 will be equal to 4 times di. So if you will try to write this here, so what you will observe, your specific surface area will always be reduced by a factor of 2 if you will take a coarser version of aggregate. Okay, so suppose you have sieve 0, which is 75 micron, and sieve 1, which is 150 micron. So for that, if my particle is in between that, my specific surface area will be this. However, if I like simplify this formula for all aggregate in the batch, I can write this as 565.7 into p naught plus p1 by 2 plus p2 by 4, like this. Here p is the percentage of aggregate in zero sieve size. So 0 represents this range, 75 micron to 150 micron. 1 represent 150 micron to a higher size of sieve, then to the next higher size, to next higher size, and subsequently will divide by 2 because my sieves are arranged in a geometric progression. Okay, let's try to see how to apply these two formulas of fineness modulus and surface modulus so that you are clear with the application part. So I have this first question which is based on fineness modulus. Try to calculate fineness modulus here. We'll talk this later when we'll talk about aggregate properties, and then we will talk about deleterious substances in aggregate. Quickly try to solve this question. Okay, so let's see the answer here. So we know what is fineness modulus. Okay, so fineness modulus is the sum of percentage retained divided by total weight, which is 100% in our case. Okay, you can see total weight is here. Okay, 100%. Okay, So I can, how I can write sum of percentage retained? So it is 5 plus 15 plus 35 plus 60 plus 85 plus 95 divided by 100. So when you will do the calculation, you will get the fineness modulus as 2.95. So this is the fineness modulus of my fine aggregate. Okay. Now, how I can comment on the suitability for use in concrete? So we knew this table scale. So 2.95, it is lying in this range, very close to 2.9. So we can say they are good for concreting. Okay, they are not very fine and not very coarse. Rahul, just check your calculation again. Just sum of cumulative percent. No, it is just sum of percentage retained. You see here, cumulative percentage retained. Cumulative percentage retained means addition of this percentage retained. Okay, so cumulative means 5 plus 15 plus 35 plus 65 plus 85 plus 95. That is cumulative percentage retained and not sum of cumulative percentage retained. Others now solve this question. So here I have a mixed aggregate sample that was sieved through standard sieve set and cumulative percentage retained. Okay, not cumulative. Percentage retained on each sieve was determined. Okay, calculate the surface modulus. Here also it is, sorry, it is percentage retained, not cumulative percentage retained. Okay. Here we need to calculate surface modulus. And you know this is the formula. So I will just copy this formula so that everyone are clear.
Hello, sir.
Yes.
I think the name of that column is cumulative percentage retained. I think, sir. The name of that column itself, cumulative percentage retained. Then you are going to means if we add directly that numbers, then it
Ah,
can.
sorry, sorry. This is cumulative percentage rating. My bad. Here also it is cumulative. So in first question, okay, so fineness modulus is cumulative percentage retained, sum of adding cumulative percentage retained. Okay, so what he said, Mr. Rahul, yeah. So what you said, it was correct. It was my fault. I wrote the uh, this column title wrong. So it is sum of cumulative percentage retained divided by 100 and not sum of percentage retained. Okay, sum of cumulative retained. Please correct that thing. If weights are given, okay, so if you know the weight, like if you know how much aggregate is retaining on 10 mm, then 4.75 mm, then 2.36 mm, and you know the total weight. So from that also you can calculate how much percentage aggregate has been retained on each sieve. Then you can calculate what is the cumulative percentage retained, and then you can calculate the fineness modulus. Okay, so suppose on 10 mm sieve, 5% aggregate has retained. Between 10 and 4.7 mm, 75 mm sieve, you have 10% aggregate. So cumulative percentage retained for 10 mm is 5%. For 4.75 mm, it is 10 plus 5, 15%. Then for smaller size, all the aggregate above will be cumulative retained. Okay, so like that you can calculate the cumulative percentage retained, add all the values and divide by 100. So that will give you fineness modulus. Okay, let's see the answer for this. Here, see, you have been given cumulative percentage retained. Okay, so 5% is retaining on this sleeve. Total 15% will be retaining on 2.36, 35 on 1.18. But here in the formula P naught, if we say how much aggregate is there between size 0 and size 1 sieve, how much aggregate is there between size 1 and size 2 sieve. For that we need percentage passing, okay, and not cumulative percentage retained. Okay, so how much aggregate is passing to 2.375 mm sieve and retaining on 2.36 mm sieve will give me aggregate in between these two diameters. Okay, so what we'll do, we'll first calculate cumulative percentage passing. Okay, how I can calculate that? Just 100 minus cumulative retained. So this will be 95. Then this will be 85, 65, 40, 15, 5, and 0. So this is cumulative percentage passing. And what will be percentage passing? Okay, so here I have 0, here I have 5. Okay, in between this range it will be 15 minus 5, so that will be 10. So 15% aggregate was passing through zero point 0.3 mm sieve, and 5 was passing through 5 mm 0.15 mm sieve. So how much is passing through 0.3 mm sieve, and in between 0.15, that will be 10%. Okay, then the percentage passing here will be 40 my 25 my 10 plus 25, that will be, sorry, 40 minus 15, that will be 25. Here again 65 minus 40, it will be 25. 80 minus 65, it will be 20, and 95 minus this will be 85, sorry, 85 minus 65, that will be 20, and 95 minus 85, that will be 10. Okay, so you just try to understand this calculation. Okay, 15% aggregate was passing through 3 mm sieve. Okay, and 5% of that 15%, 5% are passing through 150 mm sieve. So how much aggregate are actually passing through just the zero point 0.3 mm sieve and not passing to 1.5 mm sieve? That will be 10%. Okay, 10% will be in between the range. Okay, so this is how we calculate the percentage passing. Now, what is my sieve designation? So P naught, P1, P2, I need to know the sieve designation for that. Okay, so P naught is my this sieve. Okay, P1 is this is P2, this is P3, this is P4, and this is P5. So if you see here, I had denoted sieve like this. So P naught is my this sieve, okay, 150 mm, that is P naught, sieve 0 to sieve 1. that I represent P naught. Okay, 5% passing, and here instead of pan, I will take 0.75 micron sieve. So in between 0.75 and 0.15, I have 5% aggregate. In between 0.15 and zero point 0.3, I have 10% aggregate. Zero point 0.3 and zero point 0.6 mm, I have 25% aggregate. So this is how P naught, P1, P2, P3, P4, and P5 sieve designation is done. Now I know percentage passing through P naught is 5, then P1 is 10, P2 is 25, P3 is 25, P4 is 20, P5 is 10. So what I will do in this formula, I will just write 565.7 times P naught, that is 5, plus 10 by 2 plus 25 by 4 plus 25 by 8 plus 20 by 16 plus 10 by 32. Okay, so this is how I will write this equation. Okay, I will just remove this part. Okay, and this value of specific surface area, it will come out to be, when you will multiply, it will come out to 11844 per centimeter. Okay, this will be your specific surface area. Okay, clear with the calculation? Assignments out we will discuss at the end. Okay, I guess this assignment is not yet submitted by you, so maybe next week I will be able to discuss. I can't discuss the assignment before submission date. Okay, for now just try to understand this question. Any doubts in this question? Okay, so from cumulative percentage retained, we calculated percentage passing, and that percentage passing we used in the formula and calculated the surface modulus. Any doubts? Okay, so if there are no doubts, I will move ahead. But still, if anyone has any doubt, they can wait till the end of the session. I will then come back and discuss individually if someone has any doubt. Okay. Now, moving ahead, we have properties of aggregate. Like we discussed in cement, we will discuss the properties of aggregate. Okay. So, various tests on aggregates are conducted to ensure that they meet construction standards. And these testings can be categorized into physical, mechanical, and chemical properties. Okay. So in physical properties, we have sieve analysis, fineness modulus, specific gravity, water absorption, and shape testing. In mechanical properties, we have aggregate crushing value, aggregate impact value, Los Angeles abrasion testing, flakiness index, and elongation index. And in chemical properties, we have alkali aggregate reactivity and soundness. Okay. So in physical properties, sieve analysis and fineness modulus we have already discussed. Okay, we know these two things. Specific gravity, just like we saw in cement, we can determine using a pycnometer. Okay, so this is how a standard pycnometer looks like. Okay, there is a glass jar and a conical top, and there is a small opening at its peak. Okay, so we record four weights in pycnometer. W1 is my empty weight of pycnometer, W2 is my weight of pycnometer plus aggregates, W3 is my weight of pycnometer plus aggregate plus water, which is completely filled this point to this point, and W4 is my weight of pycnometer plus water completely filled till this point. Okay, so we can determine specific gravity by this formula, W2 minus W1 upon W2 minus W1 minus W3 minus W4. So here this numerator, it denotes the weight of aggregate in air, and this denominator, it will denote the apparent weight of aggregate in water. Okay, so that's why the ratio will give me specific gravity, and specific gravity is nothing but density of a material with respect to water. Okay, now next is water absorption. So aggregates have tendency to absorb water, which is very important to be determined. for a mixture design point of view. Why so? Because suppose you take a zero point 0.4 W by C ratio for concreting, but you didn't consider the water uptake by the aggregate. Okay, so what will happen from your that zero point 0.4 W water, some water aggregates will absorb, and your effective water to cement ratio will become less than zero point 0.4. It may come down till 0.36 or 0.38 something. Okay, now this change in W by C ratio, it can significantly affect your mechanical and durability properties of concrete later. So it is important to determine the water absorption of aggregate so that you can use the correction. So suppose you wanted to take 4 liters of water for your concreting, and you are assuming this water based on a certain W by C ratio. So if you know the aggregate absorption, water absorption by aggregate, what you will do, you will apply standard correction to this 4 liter by suppose x liter extra you will take, and this x liter will be taken up by the aggregate. So your W by C ratio won't be disturbed. Okay, it will be maintained as it is. Okay, so that's why this determination of x, that is water absorption of aggregate, is important. Okay, and it is simply determined by recording the difference between the saturated aggregate weight minus oven dried aggregate weight. So saturated means my aggregates are completely absorbed in water, and oven dried means when there is no water inside the aggregate. So difference of those will give me the water absorption of the aggregate. Now we have mechanical properties of aggregate, where first is aggregate crushing value aggregate crushing value testing. Okay, so this test is performed as per IS 2386 past for part 4 guidelines, and this is used to assess the strength of aggregate. So each of the mechanical properties that I will discuss today, they will have a specific purpose. So crushing value is used to assess the strength of my aggregate. Okay, so how we do this testing? So we select materials passing through 12.5 mm sieve and retaining on 10 mm sieve. Okay, so in between this sieve range, we will take our material. We'll oven dry our material for 4 hours, and then we'll crush them under a 400 kilonewton load for 10 minutes. So using a compression testing machine or universal testing machine, what we'll do, we'll apply a 400 kilonewton load on the aggregates in 10 minutes. Okay, after that we'll remove the load, we'll have the aggregates, some of the aggregates would be crushed due to load, so we'll sieve it through 2.36 mm sieve and we'll determine the percentage passing. Okay, so generally for good aggregate, the percentage passing should be limited to 25 to 30% and not more than 30%. Okay, now based on the quality of aggregate, my strength of aggregate can change. So this test will ensure that the aggregates that I am using it, they are of good strength. Second is the aggregate impact value testing. So, okay, this test is again performed using as per IS 2386 Part 4 guideline, and this is used to assess the toughness of aggregate. So, first we saw the strength of aggregate, second we are seeing the toughness of aggregate. Okay, again for this, I will select the aggregates in this range 12.5 mm, 10 mm. I will oven try the aggregate for 4 hours, but this time my testing setup is different. So, this is the testing setup for impact value. So I have aggregate that are loaded here. Okay, in this cylinder I have completely filled the aggregate in 3 layers. Okay, 3 layers for proper compaction. I filled the aggregate, and I have my this load here. Okay, and there is a key here. So what happens, I have a stand.
Sir, I want to know that one thing. What is the name of this machine?
This is an impact value testing instrument, aggregate impact testing.
Okay, okay,
Okay, this diagram you can find in the standard also, IS 2386 part 4. Okay, so as per standard, there is a specific design that is given. Okay, of this
okay,
height
sir.
between the load and the aggregate, this collar, release law, and everything you can see here. It is detailed drawing that is given. Okay, the diameter of my container where I will fill the aggregate, the diameter of the hammer which will hit on the aggregate, the distance between the hammer and the aggregate. So all these sizes are fixed so that whatever value we are calculating, it is as per a standard. And based on the location, the value should not change. It should just change because of the quality of aggregate. Okay.
Okay, sir.
Okay, so I have a standard hammer here, okay, which I will make to fall 15 times under its self weight. So there is a lock in key here. So what happens when I lift my assembly at the top, the key opens and the hammer falls on the aggregate. Then again I will raise the hammer till the top. The key will open, the hammer will fall on the aggregate freely. Free fall will happen. So that I will do 15 times. After 15 times, my aggregate, some of the aggregates will be crushed, some of the aggregate will remain as it is. So I will determine the percentage passing through 2.75 mm sieve, and that I will determine, and those values should be in this range 25, 30 and 45% for concrete used for flooring, pavement and for other use. So as per the percentage passing that I am recording, I can characterize my aggregate where it can be used. Okay. Third is the abrasion testing. So that is performed using Los Angeles abrasion testing machine. This test is again you performed as per IS 2386 part 4 guidelines, and this is used to assess the hardness of aggregate. Okay. So what we do in this testing, we produce an abrasive action using a standard steel balls, which when mixed with aggregate and rotated in a drum for a specific number of revolution will cause impact on the aggregate. Okay. So you can see here I have two tables that I have taken from IS 2386. Okay, I will just enlarge those tables. Okay, so I have this table 1, okay, and I have this table 2. So in this, we don't, like for other two testing we saw, we take a material passing to 12.5 mm and 10 mm. Okay, but here we don't do like that. Okay, suppose I have a aggregate batch, 1 kg aggregate I have. What I will do, I will first do the sieve analysis and I will see in which category my aggregates are lying, whether they are of grade A, B, C, D, E, F or G. Okay, based on the grade, okay, I will determine how much quantity I need for each grade. Okay, suppose I have an aggregate batch and I want it to be of grade A, then I will take 1.25 kg of this much passing range, 1.25 of this, 1.25 of this, and 1.25 of this. So in this way, I make a particular grade rather than taking a fixed grade 12.5 mm passing and 10 mm retaining. I will make a particular grade of aggregate, okay, based on the values given in the code. And based on the grade that I have made, number of steel balls that should be taken will be determined. So for grading A, I will require 12 steel balls. For B, I will require 10, 11 steel balls. For C, it will be 8. For D, it will be 6 and so on. Okay. So for grading A, B, C, D, machine is rotated for 500 revolution, and for grading E, F, G, machine is rotated for 1000 revolution. Okay. So this is what mentioned in the code. Okay. And this might be done so that whatever grade I am picking, they are all making a fixed abrasive action on my aggregates, okay, and properly taking into account all the things. So like I have written here, first grading of aggregate, I will determine whether I need A, B, C, D, E, F, G, whatever grade I want, that I will determine. I'll take the appropriate weight of aggregate and amount of aggregate based on the this table and this table. Okay, and I will rotate the machine at a speed of 30 to 33 revolution per minute for a specific number of rotation. So for A, B, C, D grade, I need 500 revolutions, and for E, F, G, I need 1000 revolution. That is what mentioned in the IS guideline. Okay, and after the revolution, what will happen? This is my Los Angeles aberration testing machine. So this is the lid. This I will open. I will pour my aggregate inside. I will pour my steel balls inside, and I will rotate this drum. Okay, for a specific number of revolutions. So what will happen? My aggregates and aggregate, they will hit each other, and my steel balls will hit the aggregate. My aggregate will hit the surface. My steel ball will hit the aggregate and the surface, and in this way, aggregates will be rubbing. Okay, and when they will rub against each other, so they will break, or they will start converting into powdery substance. So after my specified number of revolution, what I will do, I will take out all the aggregates in this pan below, and I will sieve the aggregates and I will determine percentage retaining on 1.75 mm sieve, and that will be used to determine my abrasion resistance. Okay, so I can quantify of how much total weight my aggregates were retaining on 1.75 mm, and that will be my abrasion resistance of aggregate. Okay, so this is how this test is done. So I will urge everyone to just go through this code, IS2386 part 4. So in this you will find all the three aggregate testing, and once you will read the code completely, you will get more better clarity of the testings. Okay, but most of the things we have discussed, so the major part I have discussed in the session, the same you will find in the code. For flakiness elongation index, we have already seen this thing. Okay, again it is performed as per IS2386, but this time part 1. Okay, so flakiness index is determined by percentage of weight of particle that are whose least lateral dimension is less than zero point 0.6 of their mean size. So this is the tool that we use to determine the flakiness index, and elongation index is defined by the percentage that is more than 1.8 times the mean dimension. So mean dimension compared to mean dimension 1.8 times more the particle is, that is my flake elongation index. So what I do, I will take each aggregate grain and I will determine the size, and then I will record the size, and then later on I will see how much aggregate are more than 1.8 times the mean dimension, and that will be my elongation index. Similarly I will do for this. Okay, flakiness index. And we have chemical properties of aggregate. Okay, here we have alkali aggregate reaction. So this thing I will talk later on when we will talk about durability of concrete, so that you can know how silica and alkali is a problem, how they react, what problem they cause, and how they are connected with the durability of concrete. So that complete thing we will discuss when we are talking about durability of concrete. But for now, just remember, my aggregates should be an inert component of my concrete. However, if my aggregate are not inert, they have some reactive silica. So that reactive silica, it reacts with alkali and they form a gel, which is expansive in nature, and that expansive gel causes cracking in aggregate. That is not desirable. So that's why we need to determine the chemical properties of aggregate also. More we will discuss in the durability class, not right now. And regarding soundness, so soundness, as we know, it is the volume change in a system which can happen due to frost action, thermal action, or wetting drying cycles. Okay, now in a concrete, I want that thermal conductivity and coefficient of thermal expansion of my aggregate and cement should be same. Okay, and for aggregate, these value will depend upon the type and the moisture content of aggregate. Okay, if the thermal expansion coefficients are different, so what will happen? Compatibility of my system will be an issue. Okay, and that can cause some volume change in my system. So to avoid these issues, impurities in the aggregate should be minimized. Okay, the more will be the impurities, the more will be the difference between the thermal coefficient of thermal expansion, and higher will be the chances of volume change and soundness issue. So impurities like clay lumps or shales or wood coal, they can lead to pitting and scaling in aggregate. That should be minimized. And mica and gypsum sulfate and sulfides will also be avoided. If you will avoid these impurities in aggregates, then soundness issue won't arise in the aggregates. Okay. Now try to answer these three questions. And in the meantime, if anyone has any doubt in the content we have just discussed on property of aggregate, they can ask. I will wait for a couple of minutes for you guys to answer these questions, and then we'll move ahead. Numerical on surface modulus. Okay, I will repeat at the end, okay, because we have moved ahead. Or let's see right now only. So here, just remember what is surface modulus. This is the formula for surface modulus. 576.7 times P naught plus P1 by 2 plus P2 by 4. Now P is the particle in the range of a particular sieve. So what I define, P naught is my particles which are finer than 0.15 mm but coarser than 0.075 mm. Okay, similarly p1 is the particle in this two size range, p2 is the particle is in between this two size, p3 is the particle in between these three size. This is how we denote a sieve. Okay. Now here in the question I had cumulative percentage retained, but for this values for the values for surface modulus, I need particle in a particular range of size. So that's why I determined percentage passing. Okay, so from cumulative percentage retained, we calculated percentage passing, and then these value I did using the sieve size that I know, I placed in the formula and calculated the surface modulus. Just try to read this slide again. Okay, the slide where we discuss surface modulus, the how the this formula came up, and then do this question on your own, you will get the answer. Okay, just go through this content again. You will have the session recorded, recording available with you. Just go through this session again, and if still it is not clear, then ask me, I will tell you. Okay, for now just focus on these three questions. Anyone who knows the answer, just write in the chat box so that others can still think about the answer.
Good evening, sir.
Yes.
Sir, I have a question regarding this gradation, sir.
Okay.
We have the
Can
standard.
you wait till the end of the session, because gradation we have passed quite like 10-15 minutes ago. So just focus on the content right now. At the end of the session we will discuss. Okay. Just
Okay, sir.
stay in the meeting at the end of the session, and then I will go back to your doubt.
Okay, sir.
Okay, let's see the answer. For question number 6, the specific gravity of aggregate is crucial in mixture design. A higher specific gravity generally indicates, so answer is very simple. Higher specific gravity means higher density and strength. So more is the specific gravity, denser is my aggregate, so more strength of aggregate I have. Okay, so answer will be B. Then soundness test of aggregate is conducted using which chemical solution? So this, I think you had this discussion in the live session. So I have directly taken from that so that I can know, I can just quickly discuss about that part. So the chemicals that are used to conduct soundness test are sodium sulfate and magnesium sulfate. Okay. So this is the answer for this question. Why? Because they can cause the formation of a salt crystal within the aggregate pores, and that salt crystal will lead to expansion, possible disintegration in aggregate if they are not durable. Okay, so using these two chemicals I can see whether my aggregates are durable or not, because they can cause formation of salt crystals within the aggregate pore. Okay, and if that crystal is formed, there will be expansion which I can detect. For third question, aggregates with higher surface roughness and angularity generally results in. So answer will be C, higher bonding with the cement base. So we know higher is the angularity, better is the strength of my concrete, because the better is the packing, and higher surface roughness will result in better cement properties. Okay, so lower strength won't be correct, higher workability won't be correct, because packing is more, so workability may reduce, and lower permeability can also be right. Okay, but the most appropriate answer will be higher bonding with the cement paste. Okay, so this is from the last session. If anyone remembers our discussion in the last session, we talked about how angularity will affect the, how the shape and the size of an aggregate can affect the property of aggregate or property of concrete. Okay, now let's move ahead. Okay, so now let's start with the next part of the discussion, that is admixtures in concrete. So in the first session, we talked about composition of concrete, in which we saw aggregates are optional entities. Okay. However, in many countries, a mixture design of concrete which contains no admixture is nowadays an exception. Okay, so this is the importance of admixture in concrete. Okay. Now, why admixtures are needed? Because they are capable of imparting considerable physical and economic benefits to concreting. Okay, how they impart these benefits? By enhancing the workability, so they are useful for pumpable concrete in large construction project. By increasing the strength and durability, how they increase strength and durability? By replacing water and thus allowing us to make a denser concrete. By making a suitable special purpose concrete, like for urgent repair or in hot weather or in mass concreting, using admixture we can make a special purpose concrete. And by making concreting cost effective and sustainable. Okay, although these admixtures are not cheap, but they can still result in indirect saving by reducing the cement content without compromising on the strength, by lowering the total construction cost or by lowering the labor cost. In these way they can make concreting cost effective and sustainable, though they are expensive, but still they can cause these beneficial effects. Okay, now, admixtures are categorized into two types. We have chemical admixtures and we have mineral admixture. Today, we will talk about chemical admixtures. Okay, so how we define a chemical admixture? So, it is basically a cement product which is added to concrete mix in quantities no larger than 5% by mass of cement. So this is the limit of how much we use an aggregate, an admixture, during mixing or prior to placing of concrete, for the purpose of achieving a specific modulation or modification to my normal properties of concrete. So admixtures, chemical admixture are basically chemical products which are added in no more quantity than 5% by mass of cement, and they are added during the mixing or before placing of concrete to achieve a desired property in concrete. Okay, my chemical admixtures are classified into different categories based on their function in concrete. There can be their function can be the chemical interaction with hydration, which are known as accelerators and retarders. They can cause adsorption on cement surface, causing better particle dispersion, which are known as superplasticizers and plasticizers. They can affect the surface tension of water, which are known as air entraining admixtures. They can affect the rheology of water, which are known as viscosity modifier. And there can be special chemicals acting on hardened concrete, like corrosion inhibitors and water repellent. Okay. Generally, all these categories of admixture they are present in the liquid form, so that they can rapidly disperse in a uniform manner during mixing. Okay, so that's why they are present in a liquid form in general. Like most of the cases will be liquid form. So first, let's see dispersing admixtures. Okay, that includes plasticizers and superplasticizers. Okay, so dispersing admixtures are used in concrete to improve the workability by reducing the water content without affecting the consistency. Okay, so what they do, they improve the workability of concrete. Workability means the flowability of my concrete. Okay, flowability. Okay, how? By reducing the water content. We know more will be the water, better with the workability. But if I will increase water, I will compromise on strength. So what these admixture do, they help us to improve the workability by reducing the water content. Not even maintaining, reducing the water content without affecting the consistency of my concrete. Okay, and how they act, how they do this, they help to disperse the cement particles more efficiently, leading to lesser water demand and a denser and a stronger mix. Okay, now my dispersion, this I will explain in the next slide in detail, how what the statement means. Okay, these admixtures fall into two main categories. I have plasticizers, which are normal range water reducers, and I have super plasticizers, which are high range water reducers. Okay, and why these admixtures are important? Because 60% of the chemical admixture that is used in concreting are dispersing admixtures. Okay, so these are the most important category of chemical admixtures. So plasticizer or water reducing agents, they improve the workability of concrete by reducing the amount of water needed for a given slump. Okay, and their key properties are water reduction. They can reduce the water content by 5 to 15% while maintaining the workability. They can improve the strength by reducing the water to cement ratio. Okay, they can better the workability, which can make placement, mixing and finishing of concrete easy, and they can reduce segregation and bleeding. Okay, which can improve the cohesion and uniformity of a mixture. Segregation means in a concrete, when my aggregates, cement and cement paste, they separate out. Okay, that is known as segregation. And bleeding means when my water is coming at the top. Okay, so suppose I have a mold, I have done concreting, okay, and I have done a lot of compaction, or if I have used a lot of water. So what will happen, my water has a lower density compared to cement and aggregate. Okay, water specific gravity is 1, cement is 3.15, aggregate is 2.7. Okay, so water is lighter than both the things. So when I will compact the system, what will happen, water can bleed and come to the top. So that is known as bleeding. Okay, so using plasticizer, I can improve the cohesion and uniformity of the mix also, and I can reduce the chances of segregation and bleeding. Okay, some of the commonly known plasticizers are lignosulfates, hydroxylated carboxylic acid, and polycarboxylate. Okay, we'll see later on after a couple of slides their structure also. And their application is to use in normal strength concrete, precast elements, and pavement, and they are suitable for moderate improvement in workability and strength. So that's why they are known as water reducing admixtures. Okay, and plasticizers. Second is super plasticizers and high range water reducing agents. Okay, so super plasticizer provides a much higher degree of water reduction compared to normal plasticizer, and allowing for extremely fluid and high strength concrete. Okay, so their feature is they are high water reduction capacity. They can lower the water content by 15 to 40%. Earlier we saw 5 to 15%. Here we have 15 to 40%, making concrete highly workable. They are self-leveling properties, so they produce a flowing concrete which doesn't require any vibration or compaction, I can say. Okay, they helps in making high strength and durable concrete. So if I will reduce high range waters, reducing admixture, I will require much lower water in my concrete. So if my water is low, my W by C ratio will be very low, so my strength will be more. So that's why they are used for making high strength or high performance concrete, and they result in better compaction. They reduce the voids, leading to a denser and the impermeable concrete. So common examples are sulfonated minimal formaldehyde, sulfonated naphthalene formaldehyde, and modified polycarboxylate. So these are commonly known super plasticizers, and they are used for high strength concreting, self compacting concrete. In precast elements they are used. In pumped concrete for high rise building we use that, and in mass concreting like bridges and dams we use high range water reducing admixture. Now, what is the science behind these admixture? How they are able to disperse cement particles? How they are able to like act as a water reducer? Okay, so these water reducers and or plasticizer, they generally belong to a dispersant family. Okay, and their composition has a water reducer which is known as a surfactant. Okay, they have a long chain organic molecule which has a polar hydrophilic tail attached to a non-polar hydrophobic organic chain with some polar groups. Okay, so these admixture has two components. Okay, these are organic elements. Okay, they are hydrocarbon chain which with some inorganic elements attached to it. So those chains have two elements. There is a hydrophilic part, which is a water attracting part, and there is a hydrophobic part, which is a water repelling part. Okay. Now mode of action, how they act. The cement particles are dispersed due to by electrostatic dispersion. Okay, so we'll see in the next slide what this means. For now, just remember they have two parts: hydrophilic part and hydrophobic part. Okay. And with the progress of hydration, the electrostatic charge diminishes and flocculation of hydrated product occurs. Okay, so these are like initially they will show their action, later on they will act as a normal material its own. Okay, so this is how their structure looks like. So we talked about lignosulfate. There's a long chain of polycarbon, hydrocarbon, and you have a hydrophilic group, CO. Here you can see hydrophilic group is there. In SNF, sulfonated naphthalene formaldehyde, you can see this is the as hydrophilic group, and this is the hydrophobic part. Here you can see this is the ester part which is hydrophilic, and the rest of the chain is hydrophobic. This is polycarboxylic ether. And here you have sulfonated minimal formaldehydes, which structure looks like this. Okay, so here again you can see this is the hydrophilic part. Okay, we saw hydrophilic part water attracting such as CO minus, SO3 minus, NH3 plus. These are all hydrophilic part, and hydrophobic part are the organic chain. So this chain of hydrocarbon, these are hydrophobic part. Okay, now how they act with the cement grain. So if we just see a simple cement plus water system like shown here, okay, so my cement grains are not separated. They are naturally clustered together to a flock which traps water. Now, why this flock is formed? Because of van der Waals force of attraction. Okay, there can be two things. There can be attraction or there can be repulsion. In cement, I have cationic charges that are present on my cement grains due to free valence at the surface of cement particle due to calcium, aluminium or silicate ion. Okay, now these charges they can repel each other. However, the van der Waals force of attraction between the particles they dominate over this repulsion and thus flocks are formed. Now, when there is a flock which is formed, my water can trap between the cement, and this water will me, this water will appear to be not contributing to my hydration because it is trapped. Now, when I add SP, a super plasticizer, what happens? My SP has a polar group, which is water. I have a hydrophilic group, which is water loving, and I have a hydrophobic part, which is water repelling. Okay, so polar group is known as water loving, non-polar group is hydrophobic or water repelling. Okay, now what happens? These sp molecule they try to cover the cement grains, okay, such that the non-polar groups will cover the cement grain while the polar group will disperse out towards the water. Okay, so what happens, due to the charges present on this dispersion of non-polar group, they start to repel each other, and when they repel each other my cement grains get separated, and the water that was stuck inside my cement grain it is released, and thus I get a better workability in my concrete. Okay, so they cause the due to their repulsion, they cause my cement particles which were like flocculated here to disperse, and they release the water that was trapped, which is now available for hydration. Okay, so because of the dispersion of that non-polar group, the cement particle repel each other, and thus cement grains are separated, and the trapped water becomes free and available for hydration. Okay, so in this slide, it shows how a water reducing admixture repel cement grain. Okay, and this repulsion is based on two mechanisms. There is electrostatic repulsion and there is steric hindrance. Okay, electrostatic repulsion is due to zeta potential. So zeta potential is nothing but the charge that exists on the surface of a tiny particle in a liquid like cement and water. Okay, so it controls how my particle interact, whether they will repel, they will attract, or they will clump together. So if I have a high zeta potential, particle will repel each other. If I have a low zeta potential, particle will attract each other. Okay, so the negative charges that are imparted by a plasticizer, they have a high zeta potential which makes cement grain to repel each other. That is known as electrostatic repulsion. And steric hindrance is due to the bulky polymeric side chain. Okay, so we saw a couple of slides ago, there can be a bulky side change in my super plasticizer. Side chain is this hydrocarbon part. If this is very bulky, so what will happen? They will prevent cement particles to physically agglomerate or come together, and that can also cause dispersion. So that is known as steric hindrance. The hindrance caused due to the bulky side chains which are not interacting with. Okay. So this is the two mechanism in which a water reducing admixture can repel a cement grade. Okay, this slide just summarizes the action of a water reducing admixture. Suppose you made a concrete which having a compressive strength A and workability V. Now, if you want to increase the compressive strength, what you will do? You will add more cement. Okay, so if you will add more cement, your W by C ratio will decrease and your compressive strength will increase. So remember, compressive strength and W by C ratio have this inverse relation. Okay, lower is the W by C ratio, higher is the compressive strength. Why? Because lower W by C ratio means lower porosity and therefore higher is the compressive strength. Okay, so if I need to increase the compressive strength, I will add more cement. So my compressive strength will increase, but my workability will remain the same because my water is the same. And if I want to increase the workability, what I will do? I will increase the water and I will increase the cement both. So that my W by C ratio is the same. So strength will be the same. But since I have more water, my workability will be more. Now, if I will use a water reducing admixture, what will happen? I can make a concrete of compressive strength A and workability B by reducing both water and cement and keeping the W by C ratio same. Okay, so what I will do? I will reduce water also and I will reduce cement also and I will add a SP. So what will happen? Since my W by C ratio is the same, strength will be the same, but since I have reduced water, workability might have influence, but since I'm adding SP, my workability will be maintained. Okay. Now, if I want to increase the compressive strength, what I will do? I will reduce the water. I will keep the cement same. Okay. If I will reduce the water, W by C ratio will come down, so my strength will increase. And since I've added SP, so my workability won't be affected. Okay, it will compensate for the less water that is there in the system. Now, if I want to improve the workability, what I will do? I will keep the water to cement ratio same and I will add SP. So, what will happen? My W by C ratio is the same, the strength will be the same. But since I have added SP, there is more dispersion, so my workability will improve. So, you can see in this way, a W water reducing admixture can be used for different need. Okay, if I want more strength, I can use a WRA. If I want more workability, I can use a WRA. And if I want same strength and workability, then also I can use a WRA, but it will make my concrete more cost effective and sustainable. Now try to answer these three questions. And in the meantime, if you have any doubts, just post your queries in the chat box regarding water reducing admixture. So generally, these admixture have a very low range, like 1%, 2%, 5% is a very large quantity. Generally, we add 1% by weight of cement or 1.5% by weight of cement. Up to that limit only they go. Maybe 2%, 2.5% they can also go, but they are added in a very small quantity, not much. Alkali aggregate reaction we'll see when we'll talk about durability, then we'll talk about that. So it is basically alkali which is present in the pore matrix due to cement hydration. When it reacts with aggregate, they cause gel formation. That gel is expansive in nature, which can cause cracking in concrete, and that reaction is known as alkali aggregate reaction. Okay, so if my aggregates have reactive material, reactive silica in it, it can give rise to alkali aggregate reaction. More on this we'll see when we'll talk about durability, so that you are clear with what is cracking, what is happening due to the system, due to cracking, and all those things. For now, just try to answer these three questions, and if you have any doubt regarding WRA, ask that.
Hello, sir.
Yes,
Sir, last week live session PPTs are not uploaded in that NPTEL website. Which are
that thing
not available
NPTEL
in the
generally
site.
do, so I don't have any update on that. You need to contact to the NPTEL team itself.
Okay, sir. Actually, because I have going to that website, so it is not available.
Just drop them a mail, ask them when the session
Okay.
recording will be uploaded, and then you will be good.
Recording is uploaded, but the PPT is not there.
Then you need to contact them whether they will share the PPT or not, or they will just share the recording. That thing they will not
Okay,
be
sir.
there.
But the first week live session PPT is also that
Then they will
available,
share.
and
Then
record
they
is
will
also
share.
available.
They might take some time, but they will share.
Okay, sir. Yes, thank you.
Try to answer these three questions quickly now. Let's see the answers now. Okay, so for ninth question, which test is most appropriate to for measuring the effectiveness of a super plasticizer in maintaining the workability? That will be slump retention. Okay, so what how much slump it is giving? Slump is the flow of my concrete, so that we can use to determine the workability over time. Okay, so suppose just after mixing, I am getting a slump value of say 150 mm. 1 hour after mixing, what value I'm getting? 2 hours after mixing, what value I'm getting? So that thing can tell me what is the workability over time, whether it is able to retain its workability, retain its slump, or whether it is not retaining its slump. Okay, so answer will be B, slump retention. How does the molecular weight of polycarboxylate superplasticity affects its performance? So for this answer will be A. Okay, so this is a very general statement that you can remember. So higher molecular weight leads to better steric repulsion and a longer slump retention. So generally say super plasticizer having a higher molecular weight, they are high range water reducing admixtures. Okay, so if I have a higher molecular weight, what will happen? There will be more steric repulsion, and if there is more steric repulsion, there will be a longer slump retention. Okay, so 10th is A. Okay, 11th, what happens if too much superplasticizer is used? So they can cause excessive bleeding and segregation. So initially we have talked about this. Okay, too much of superplasticizer is also not desirable because it will cause my water to bleed and it will cause segregation in my system. So that's why I need to limit my superplasticizer up to an extent when I'm getting the maximum efficiency, and that's why it is limited to just 5% by weight of cement and not any quantity. Okay, so for this also there are different testings that are done to determine the maximum capacity. Okay, now after superplasticizer we have set controlling admixture, which are retarders and accelerators. So as the name suggests, they can control or manipulate the setting behavior of my cement, or we can say setting behavior of my concrete. And what is the basic mechanism behind this? So they interfere with the cement hydration. Okay, if they will interfere with the hydration, they can control the setting. And how they do that? By altering the rate of dissolution of cement grain during hydration, either by speeding it up or slowing it down. So an accelerator, it speeds up the dissolution rate, and the retarder will slow down the dissolution rate. So it will retard the setting, it will delay the setting. An accelerator will increase the setting, it will make setting happen sooner. Okay. Now the choice, what type of set controlling admixture I need, will depend upon the application requirement. An accelerator may be required in cold weather concreting, where my concrete is not setting. Okay, so I need an accelerator to set the concrete. Or when I need a early strength gain, then I need quick setting, then I will require accelerator. Or when I need a early removal of foam work, then I will need an accelerator. A retarder is used in hot weather concreting, where due to high temperature of the surrounding, setting is happening sooner than required, then I will require a retarder. Or when a concrete mix is needed to be remain in workable state for a longer period, suppose my mixing plant and my casting area are spaced apart, I will require a retarder so that my concrete is remaining workable for a desired time period. Okay. Or for reducing risk of cold joint between large pores. So suppose I have a very long column in which I am pouring concrete from the top. I have poured till the midpoint, then from the casting batch I am mixing the concrete and then I am pouring. Now if the time between the two is more, what will happen? My first pour will, it will start to set, and then I am pouring the second batch. So there will be cold joint that will be created in between, which is not desirable. So using retarder, what I can do, I can delay the setting of the first batch, so that when the time when I pour the second batch, both will be uniform and there will be no cold joint that is there in between. So for that also I can use retarder. Okay, what is the basic chemistry behind the accelerator? So in cement hydration, we have cations and we have anions. Okay, cations are calcium ions, anions are silicates and aluminates. So among these, silicates rate of dissolution is slower compared to calcium and aluminates. So what an accelerator do? It increases the ionic availability by introducing calcium ions, chloride ions and nitrate ions to the system, and it lowers the energy barrier and it accelerates the reaction, cement hydration. Okay, it can be hardening accelerator, which increases the resolution of calcium silicates and increases the CSH formation. If it does this, it is known as hardening accelerator. And if it allows C3A to react faster and not react with gypsum, then it is a set accelerator. Okay, so we saw if C3 reacts with water, it causes flash setting. However, if we add gypsum, we can reduce the chances of flash setting. Okay, so if I want to setting to appear soon, I need C3 to react with water and not with gypsum. So a set accelerator can make that happen. So that's how it can accelerate the setting. Commonly known accelerators are chloride based, which are HCaCl2 and NaCl, and non-chlorides based are inorganics, nitrates and nitrites, thiocyanates, thiosulfate, and organics like amines, carboxylic acid. These are all accelerator. We don't prefer to use chloride accelerator because they can cause risk of chloride induced corrosion, which we'll see later on in the durability. So these are not desirable. Generally, we use non-chloride accelerators nowadays. And a retarder, it slows down the hydration reaction by delaying the formation of hydration products. Okay, it can do this in three ways, either by absorbing on the cement particle. So if it absorbs on the cement particle, it will slow down the interaction of water with the cement. Okay, and will slow down the hydration. Another way is it can form calcium complex, which can reduce the free calcium ions available for hydration, which can reduce the hydration rate. Or it can delay the C3 hydration. If the C3 hydration is delayed, the setting won't happen. So it can extend the dormant period that we say. Okay, in these three ways, a retarder can act. Okay. After this, we have air entraining admixtures. Okay. So as the name suggests, these admixture allows controlled quantity of small uniformly distributed air bubble to be introduced during mixing and remain after hardening. And they are mainly used so that we can improve the freeze thaw resistance to prevent cracking due to volume expansion in cold weather. Okay, so why would we need such admixture? like air voids in concrete will hamper the compressive strength. Why we are introducing air voids? Okay, these are required in freeze thaw to improve the freeze thaw resistance. Now, what is freeze thaw mean? Okay, so freeze thaw means that, like, when my in cold climates, what happens? Water inside the pores, they freeze. Okay, and when water converts into ice, there's a volume expansion by about 9 to 10%. Okay, since my concrete is rigid material and it has a very limited space to accommodate such expansion, the ice that is forming inside the voids, it can cause pressure on my matrix. Now, my concrete is not designed to handle this. Okay, because there is no air void which can account for this expansion and contraction that will happen, like freezing and then melting, then freezing, then melting. It will cause continuous expansive stress on my system, and there is no air inside my concrete to accommodate that expansion. Okay, so if there is no air, what will happen? There will be cracking inside concrete which can cause damage to the concrete. So, to improve this property in cold weather, we use air entraining admixture in the concrete. So, these admixtures, what is the chemistry behind them? So, these are basically surfactants which have hydrophilic head and a hydrophobic tail. So, surfactant, what they do, they reduce the surface tension of water by absorbing on the liquid gas interface. Okay, so these are surfactants you can see here. Okay, so what happens? The hydrophobic part surrounds the air. Initially, I have a air void in my cement matrix. Okay, what they do? They surround the air void and they prevent them from merging or breaking. Okay, and in this way, they stabilize these air voids inside the concrete system. Okay, so these air voids are not broken, but they are like a separate entity or separate units that are present inside the concrete system. So when there will be some water freezing or expansion, what will happen? There will be these air voids which can account for that freezing and expansion. There will be more space inside the concrete to take into account that extra volume that is forming. Then we have viscosity modifying admixtures. So these are used to enhance the viscosity of my concrete. Okay, and they are used to control segregation, bleeding, and flowability, making a concrete self consolidating concrete. Okay, how they act? They are generally long chain polymer molecules, and they modify the rheology of my cement paste. Okay, how they do that? They absorb on water molecule. Okay, they associate with each other and they further, like, they basically act on water. Okay, so what they do, they bind the water molecule and fix some part of water. So suppose I have w grams of water. From w grams, this viscosity modifying admixture will fix some gram. Okay, so if I have less water, what will happen? My viscosity of my system will be modified. Okay, and they will increase the viscosity. Now, these molecule, apart from fixing the water, they can develop attractive forces and further block the motion of water, which can increase the viscosity of my system, and they can cause winding in between them, which can cause the increase in viscosity. If I will visualize this thing from this diagram, you can see here. Okay, so I have this diagram. Okay, if I have no viscosity modifier, what will happen? When we do a slump test, my concrete is like this originally, but within 5 seconds, my concrete completely collapse. However, if I have a viscosity modifier, if I have a very high viscosity in my system, even after 5 seconds, my slump is not collapsing because it is a very viscous material. In higher viscosity means lower is the flowability of my material, so it will be able to retain its shape to a more extent, more time, and that is how viscosity modifying admixture work. Okay, now we have other chemicals also which are not that important but are also categorized in chemical admixture. We have shrinkage reducing admixture, which are used to reduce drying, shrinkage, and cracking. Okay, they have lower surface tension on pore mat. They lowers the surface tension of pore water and reduce the internal tensile strength, and these are the examples for that. We have waterproofing admixture, which improve the concrete's impermeability, so they don't allow water to penetrate inside concrete. by blocking the pores inside the concrete and reacting with the cement to form a hydrophobic compound. So these include crystalline admixture, hydrophobic agents, and all those things. We have alkali silica reaction mitigating admixture. Okay, so they prevent expansion and cracking due to alkali silica reaction in concrete. They reduce the alkali content in concrete and bind the reactive silica in the aggregate to prevent the gel formation, like we discussed earlier. Reactive silica and uh, alkali in my cement paste, they can react to form gel, okay, which causes expansive stresses in concrete. So these admixture, what they do, they reduces the alkali content and they bind the silica so that there is no gel formation. And for these examples are lithium nitrate, fly ash, silica fume, and metacoiling. So these are all alkali silica reaction mitigating admixtures. Okay, so these three are not very commonly used, but still we can categorize them as chemical admixture. I have not discussed here corrosion inhibitors. That portion I will touch up later when we'll talk about durability, because for that one needs to understand what is corrosion, kinetics of corrosion, and all those things, and then only a corrosion inhibitor action will be clear to you. So that part we'll discuss later. Okay, just try to answer these three questions, final three questions for the session. And in the meantime, others who have doubt, they can stay in the meeting and ask their questions. Okay, just try to answer these questions quickly. And if you have any doubts in the session part that we have discussed right now about chemical admixtures, you can also ask that. Okay, let's see the answer for these questions. Okay, first question is, which of the following is which of the following is a common mechanism by which a crystalline waterproofing admixture function? So how they function? By blocking the capillary force by reacting with the free line. Okay, so generally a crystalline water reducing admixture, waterproofing admixture, it penetrates the concrete and react with the free lime like calcium hydroxide and moisture to form a insoluble crystal, okay, that blocks the capillary pores and it prevents the water, it reduces the water permeability. So this crystalline admixture, it reacts with lime to form a crystalline product which is deposited in the pores, which blocks my water to penetrate inside, and that's how it shows a waterproofing activity. Okay, this is the function of crystalline waterproofing admixture. In this slide also uh, uh, I mentioned that they block the capillary pore or react with cement to form a hydrophobic compound. So second mechanism is acting in crystalline admixture. The effectiveness of shrinkage reducing admixture can be reduced in conjunction with, the answer will be air entraining agent. Okay. So why? Because shrinkage reducing admixture, they like air entraining agent, they create stable air bubble inside the concrete, and this can compromise my shrinkage control or freeze thaw resistance. Okay. Okay. So like I don't need a air bubble. Okay, if I will have more air bubble, then my shrinkage reducing part will be affected. Okay, they both can't work together properly. Okay, they both have a different working mechanism. That's why we can't use any admixture, chemical admixture together. We need to check the compatibility of chemical admixtures also. It has a different function, it has a different function. Okay, they both are not compatible with each other. Third, which type of admixture is primarily sensitive to temperature variation? Okay, so answer will be D, accelerators. Okay, why? Because accelerators are primarily, their function is to speed up the setting and the hardening of concrete. So if I have higher temperature, it can cause excessive increase in the rate of reaction, while if there is lower temperature, it can reduce the effectiveness of my accelerator. Okay, temperature is sensitive to my setting behavior. Okay, and setting behavior is affected by the accelerator. Okay, that's why it is sensitive to temperature. Okay, so this was all for today's session. We talked about aggregate grading, we talked about different properties of aggregate, and we talked about chemical admixtures. Okay.